Module 1, Lecture C, TF 2.20, Overview. By the end of this lecture, you will be able to summarize the core architectural concepts behind TensorFlow 2.20 and eager execution, identify the primary high-level APIs in TensorFlow 2.20.0 and their roles, and distinguish between stable, legacy, and experimental TensorFlow APIs relevant in 2026. Eager execution basics. Immediate tensor execution. In TensorFlow 2, tensors are executed immediately, meaning operations run and return results right away instead of being added to a separate computation graph. This makes working with TensorFlow feel more like using standard numerical tools such as Python or MATLAB. You can directly inspect values and use them in control flow as your code runs, which reduces the gap between what you write and the actual computations. As a result, it becomes easier to follow and understand what your model is doing at each step in an interactive setting. Immediate execution in TensorFlow lets you build and debug machine learning models in a more intuitive, interactive way. Because operations return real values right away, you can freely use loops, conditionals, and print statements to explore how your model behaves. This makes it easy to inspect activations and tensor shapes as you work, and to quickly spot and address issues such as exploding gradients. In a notebook environment, you can rapidly iterate by running cells, checking the results, and refining your model based on what you observe in real time. In TensorFlow 2, tensors execute immediately, so operations appear to run right away, while TensorFlow quietly handles device placement and optimization in the background. When you perform tasks like large matrix multiplications, it automatically chooses between CPU, GPU, or other accelerators, and manages data transfers without requiring an explicit computation graph. This lets you write intuitive, Python-like code that can be prototyped on a laptop and then scaled to a server with powerful GPUs. Overall, you get a simple interface to TensorFlow's engine that you can later tune for performance and deployment. Python code, immediate tensor execution. This script introduces the basics of immediate tensor execution, using only the Python standard library to keep things clear. It focuses on simple numerical operations carried out directly on tensors and highlights what you can observe as these operations run. The goal is to give a straightforward, hands-on sense of how tensors behave during basic computations without extra tools or complexity. We import the math module so we can use more advanced mathematical functions beyond basic arithmetic. This includes operations like square roots and trigonometric calculations. Using the math module lets us perform these numeric computations with better precision and reliability. There is a helper function called printTitle that is used to organize the program's output by printing section titles. It takes one input, which is the text of the title. When called, it prints a blank line and then the title, creating visual separation between sections. This makes the script's output easier to read and helps the user follow the flow of the program. This section introduces immediate numeric operations in Python by showing a simple example. We add the numbers 3 and 4, and this calculation is carried out right away. The result of this addition is stored for later use. Finally, we display the stored result so we can see the outcome of the operation. We check the type of the result from the addition to confirm that it is stored as a concrete Python integer. This shows that when we add numbers, Python not only computes the value, but also assigns a specific data type to the outcome. Understanding this helps clarify how Python represents the results of numeric operations and how those results behave in later calculations. This example introduces immediate list comprehension execution by first printing a short title, then creating a list of values using a comprehension. The comprehension goes through the numbers from 0 to 2 and multiplies each one by 2, producing a list of doubled values. These values are then printed right away, showing that the list comprehension runs immediately and the resulting data is instantly available for use. We print the length of the list called values to show that the earlier list comprehension has already created a real list with a definite number of elements. By checking its length, we verify that the data is fully available right away. This reinforces the idea that in Python, this kind of list construction runs immediately and produces a concrete result you can inspect. The tiny step function represents a simple, reusable computation. It takes one input value, called x, and returns the result of x multiplied by itself plus 1. This shows how even a small operation like squaring a number and adding 1 can be wrapped inside a function. Doing so makes the code clearer and easier to reuse in larger programs. This section demonstrates running a simple computation repeatedly in a loop. We start by announcing the section and setting a variable to 0 to store our running result. Then we perform 3 loop iterations, and in each one, we update the result by applying a small step function that squares the current value and adds 1. After every update, we print the step number and the new result so we can see how the value changes at each stage of the loop. We demonstrate a simple conditional check based on an immediate result. First, we set a threshold value, such as 5. Then we compare the current value to this threshold. If the current value is greater, we print a message saying it is above the threshold and include the threshold value. Otherwise, we print a message saying it is not above the threshold, again mentioning the threshold. This shows how a program can change its flow based on predefined criteria. We perform a simple numeric sanity check by using the math library to compute the square root of 2 and then squaring that result. In theory, this should give exactly 2, but because Python uses floating point arithmetic, the result may be slightly off. We then print the value rounded to 3 decimal places to show this small difference. This example illustrates the limited precision of floating point numbers in Python. This script demonstrates how Python executes numeric operations immediately and makes results available right away. It starts with a simple addition, then uses a list comprehension to double a range of numbers and confirms the list is ready to use. A small function is defined and called repeatedly in a loop, with each step's result printed to show that loops also run and update values immediately. A conditional check then evaluates the final result against a threshold to give instant feedback. Finally, a quick numeric check with the math library approximates the square of the square root of 2, rounded to 3 decimal places, illustrating both precision and immediacy in Python's mathematical calculations. Graph model changes. TensorFlow 2 changed how computational graphs are handled by introducing eager execution, where operations run immediately instead of requiring a separate static graph. This makes it feel more like a standard numerical library and allows you to write and debug models in a more natural Python-based style. The graph model still exists, but it is now mainly used as an optimization layer for better performance or deployment when needed. In practice, you work eagerly by default and capture computations into graphs only when it is beneficial. In TensorFlow's newer approach, your Python function or model is the main focus, and the computation graph is automatically generated from your code. TensorFlow traces the operations you write and compiles them into an optimized graph. similar to how a just-in-time compiler optimizes machine code. This lets researchers work interactively in regular Python and then smoothly switch to fast, efficient graph execution when they need large-scale training or deployment. TensorFlow's eager execution lets you write and debug models using normal Python code, including familiar loops and conditionals that behave as you expect. When this code is later converted into a computation graph, TensorFlow automatically optimizes it for hardware accelerators like GPUs and TPUs. This combination allows you to focus on clear, correct Python while the system handles graph optimizations such as efficient operation fusion and device placement. As a result, you get both intuitive development and strong performance without needing a separate programming model for deployment. Python code, graph model changes. This script demonstrates how TensorFlow models change when moving from eager execution to a traced graph function. It highlights the differences in behavior between running operations immediately and running them as part of a compiled graph. The example uses small tensors, so the outputs are easy to see and compare. Overall, it helps you understand how TensorFlow's execution mode affects the way models are represented and printed. The commented line recommends installing TensorFlow version 2.20.0 to match the rest of the script. Locking in this specific version helps ensure that the code runs as intended. Different TensorFlow versions can change how functions work or how code must be written. By fixing the version, the script reduces the risk of unexpected behavior or errors caused by version differences. We start by importing the operating system module so we can control environment settings, and we set the CUDA visible devices variable to -1 to turn off GPU usage and force TensorFlow to run only on the CPU. This is helpful when a GPU is not available or not needed for the task. We then import TensorFlow and give it the short name tf, which is a common convention that makes it easier to call TensorFlow functions throughout the script. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because different versions may behave differently. This helps with compatibility checks and troubleshooting issues in your code. The print separator function is used to clearly divide sections of output in the console. It takes one input called title and prints a blank line followed by 3 dashes, the title, and 3 more dashes. This creates a consistent visual break in the results, making it easier to see where one part of the script's output ends and the next begins. Overall, it improves readability by highlighting different sections of the program's output. We start by creating a small, constant tensor on the CPU to demonstrate how TensorFlow operations work. The computation device is explicitly set to the CPU so that all operations run there, instead of on a graphics processor. In this example, the tensor contains the floating point values 1, 2, and 3. This simple setup will later be used to compare how TensorFlow behaves in eager execution and in graph mode. In this step, we verify that the tensor X has the correct structure before doing any further calculations. We use an assertion to confirm that it is one-dimensional and contains exactly 3 elements. If the shape is different, the assertion triggers an error message that reports an unexpected tensor shape. This validation helps catch problems early and ensures that later computations work with data in the expected format. This example describes a simple compute function that operates on a tensor. It first multiplies the input tensor by 2, then adds 1 to the result. The final value is returned as the output. This illustrates basic tensor manipulation in TensorFlow using straightforward arithmetic operations inside a function. We start by demonstrating how eager execution behaves in practice. To make its output easy to recognize, the script first prints a separator labeled eager execution result. This label clearly marks which part of the program's output comes from eager execution, separating it from other results. Using this simple visual cue helps keep the different execution modes organized and easy to interpret. We call the simple compute function with the tensor x as its input, and this runs in eager execution mode. In this mode, the computation is carried out immediately, and the result is produced right away. This makes the process straightforward and lets us see the output directly without any extra graph tracing or optimization steps. In this step, we print the result produced in eager execution mode, where operations are evaluated immediately. This immediate evaluation helps with debugging and understanding how data move through the computation. We then call the NumPy conversion method on the result to turn the TensorFlow tensor into a NumPy array. This makes the output easier to read and gives a clear view of the computed values, confirming that the function worked as expected. Using TensorFlow's function decorator turns a normal Python function into one that builds a computational graph instead of running operations immediately. In this graph-based function, an input tensor is multiplied by 2, and then 1 is added to that result to produce the output tensor. This graph execution model lets TensorFlow optimize and run the operations more efficiently. We now introduce a demonstration of how graph execution works in TensorFlow using its function decorator. The goal is to compare how the same computation behaves when run as a graph versus when it is run in eager mode. To make this transition clear in the output, we call a separator function that visually marks this new section. This helps listeners follow the shift between the two execution modes as we explore their different behaviors. When we call the traced function named simple compute graph with the input tensor, TensorFlow builds an internal computational graph that represents the operations in that function. This graph structure allows TensorFlow to execute the computation more efficiently. The output of this graph-based computation is then stored in a result object that holds the final value produced by the graph. We run the traced function to execute the graph and print its result, which should match the output produced in eager execution. To make this result easier to read, we convert the TensorFlow tensor into a standard NumPy array using the appropriate method. Comparing these values confirms that graph execution and eager execution produce the same concrete results, ensuring consistency between the two modes. To highlight how a computation graph is created, we obtain a concrete function from the traced graph function. This is done by calling the method that returns a concrete function for specific input settings. In this case, we define the input as a tensor with length 3 and data type float32. Doing this lets TensorFlow capture the exact computation graph for those inputs, so we can inspect and verify the graph structure it builds and optimizes behind the scenes. We start by signaling that a graph object exists behind the scenes in TensorFlow. A helper function prints a separator labeled graph object summary to clearly mark this new section of output. This visual break indicates that we are shifting focus to the internal graph representation. Highlighting this graph is important because it underlies how TensorFlow organizes, optimizes, and executes operations. We print a short description of the internal graph object that TensorFlow creates for our function and use the type function to see the class name of this graph. This reveals that TensorFlow has built a graph representation behind the scenes rather than just running the function directly. Understanding that a graph is created is important because this structure is what allows TensorFlow to optimize and execute computations efficiently. In this step, we print a separator labeled consistency check to clearly mark a new section of the output. The goal is to verify that the results from eager execution and graph execution in TensorFlow match exactly. By comparing these outputs, we confirm that both execution modes produce the same computations. This consistency check helps validate that the model behaves reliably regardless of how it is executed. We use TensorFlow's debugging tools to verify that eager execution and graph execution produce the same results. By forcing computation to run on the CPU, we keep the environment consistent, which helps with reliable debugging. A TensorFlow check called assert_near compares the outputs from both execution modes and confirms that their values are almost identical. This validation step is important to ensure that the graph-based execution correctly reproduces the behavior of eager execution. The script ends by printing a confirmation message that tells you the results from eager execution and graph execution are the same. This final check shows that both ways of running computations in TensorFlow produce identical outcomes. It reinforces that using graph mode alongside eager execution is consistent and reliable. Overall, it assures you that either execution method will give you the same correct result. This script illustrates the difference between eager execution and graph execution in TensorFlow. It runs a simple computation that doubles the values of a small constant tensor and then adds 1, first in eager mode where operations run immediately. The same computation is then wrapped with TensorFlow's function decorator so it runs as a traced computational graph. The script prints the results from both modes, shows a brief summary of the created graph, and uses TensorFlow's assertion tools to confirm that eager and graph execution produce identical outputs. Tracing with tf.function. The TensorFlow function decorator uses tracing to combine the simplicity of eager execution with the speed of graph execution. In eager mode, operations run immediately but do not benefit from graph-level optimizations. When you wrap a Python function with this decorator, TensorFlow watches the first calls, records the operations, and builds a computational graph. It then caches and reuses this graph for compatible inputs, enabling optimized execution on different hardware. In effect, TensorFlow learns the structure of your code once and then runs it like a compiled program for similar inputs. In TensorFlow, tracing means that your Python code is first interpreted to build a symbolic graph of all the operations and their dependencies, separate from actually running them. When you first call a function, TensorFlow records the sequence from inputs to outputs as this graph. With the graph in place, TensorFlow can optimize the computation by reordering steps, removing unnecessary work, and spreading tasks across devices. This makes training large models or running simulations faster and more consistent than running the same code directly in eager mode, while still letting you write code in a straightforward style. When you use the TensorFlow function decorator, TensorFlow traces your code to build computation graphs based on input shapes and types, creating specialized graphs for different kinds of inputs. Because this tracing focuses on TensorFlow operations, regular Python side effects like printing or changing global variables may not behave as you expect. The benefit of this approach is that it produces optimized graphs that can be efficiently deployed on many platforms, while you still write code in an eager, Pythonic style. By understanding how tracing works, you can design functions that make effective use of TensorFlow's graph execution capabilities. Python code, tracing with tf.function. This script introduces TensorFlow eager tracing with a focus on how the TensorFlow function feature builds and uses computation graphs. By running the code cells, you can observe when and how tracing occurs as functions are converted into graph form. The goal is to help you understand the relationship between eager execution, TensorFlow functions, and the underlying graphs they create. The line that begins with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. rather than a piece of Python code. It is used to make sure that this exact version of TensorFlow is available before the script runs. Specifying the version is important because different TensorFlow versions can change features and behavior. By fixing the version, you help keep the environment consistent and avoid compatibility problems. We begin by importing 3 standard Python modules that prepare the environment for our script. The operating system module lets us interact with the system, for example by working with environment settings or the file system. The random module allows us to generate random numbers, which is useful for testing or simulations. The math module provides common mathematical functions and constants, such as trigonometric operations and the value of pi. Together, these imports supply essential tools the script may need later. To avoid CUDA errors on systems that may not have a valid GPU setup, the code disables GPU usage through an environment setting. By clearing the CUDA visible devices setting, it tells TensorFlow to ignore any available GPUs. This forces the script to run only on the CPU, which helps ensure it runs reliably even when no compatible GPU is present. We use a deterministic random seed so that any random operations in our code give the same results every time we run it. By setting the seed to a specific value, such as 7, the sequence of random numbers becomes repeatable. This consistency is especially helpful for debugging and testing, because it lets us recreate the exact same conditions and outcomes across different runs of the script. The script begins by trying to import TensorFlow, a key library needed for its machine learning and deep learning features. The program depends on TensorFlow to run correctly. If the import fails, it catches the error, stops the script, and displays a message explaining that TensorFlow is required for the demonstration. This makes sure the user knows the dependency is missing and must be installed before continuing. This line of code prints the version of TensorFlow that is currently in use. It reads the version information stored in the TensorFlow module and displays it in a simple format. This helps you confirm which TensorFlow version is installed and check that it matches the requirements of your script or project. This code uses TensorFlow's configuration tools to check whether a GPU is available. It does this by listing the physical devices of type GPU on the system. Knowing if a GPU is present helps you decide how to run your computations. Using a GPU can greatly speed up TensorFlow operations compared to running them only on a CPU. This code checks whether a GPU is available for TensorFlow. It looks at the list of physical GPU devices and converts that list into a true or false value. If the list is not empty, it means a GPU is present and can be used. The result is then printed to the console to indicate whether TensorFlow can run on a GPU. In this step, we create a small constant tensor in TensorFlow that holds the 3 floating point values 1, 2, and 3. We explicitly set its data type to 32-bit floating point, which is commonly used in TensorFlow because it offers a good balance between precision and performance. This simple tensor will serve as a basic example for demonstrating different TensorFlow operations later in the script. In this step, we create a new tensor using TensorFlow's constant function that holds the values 4, 5, and 6 as 32-bit floating point numbers. Its shape and data type are chosen to match an existing tensor. This ensures the two tensors are compatible and can be used together in later operations within the same script. In this example, we define a simple function called eager_add that takes 2 inputs and uses TensorFlow operations to add them together. The function immediately returns the sum of the inputs. This illustrates TensorFlow's eager execution mode, where operations are carried out and produce results as soon as they are called, instead of being delayed for later execution. In this example, we call an eager_add function with 2 tensors, a and b, to perform element-wise addition, The operation is carried out immediately, and the sum is stored in a variable called result eager. This behavior illustrates TensorFlow's eager execution mode, where operations run right away and directly return a tensor instead of building a deferred computation graph. This line of code adds 2 tensors and immediately prints the result using eager execution. It then converts the resulting tensor to a NumPy array before printing. This shows that with eager execution, operations are run right away and you see the output directly without first creating a separate computational graph. When we apply TensorFlow's function decorator to a Python function, TensorFlow traces that function and converts its code into a computational graph. Inside this decorated function, we can define operations such as adding 2 inputs, x and y. By compiling the function into a static graph, TensorFlow can optimize the computation and reuse the same graph efficiently whenever the function is called with the same kind of inputs. This leads to better performance compared to running the raw Python code each time. When we call the traced function with the 2 input tensors, TensorFlow begins tracing and compiles that function into a computation graph for faster, optimized execution. The output of this first traced call is stored as the traced result. This process shows how TensorFlow converts normal eager execution into a more efficient, graph-based execution using its tracing mechanism. The code prints the output from the first call to a function that has been decorated with TensorFlow's tracing feature, which compiles it into an optimized computation graph. It then converts this output to a NumPy array so the values are easy to read and compare. This printed result is used to check that the tracing process has correctly captured and executed the function's logic. When we call the traced function again with the same kind of inputs, TensorFlow reuses the computation graph it created earlier instead of building a new one. This works because the input tensors have the same shapes and types as before. By avoiding retracing, TensorFlow saves time and improves performance. This shows how the tracing mechanism efficiently handles repeated calls with identical input signatures. The code prints the result of calling the traced function a second time, showing that TensorFlow reuses the same computation graph when the input signature has not changed. This behavior confirms that the tracing process does not repeat unnecessarily, which makes execution more efficient. Converting the result to a NumPy array presents the output in a familiar format and helps verify that the tracing mechanism is functioning as intended. We obtain a concrete function by calling the TensorFlow function with specified input types and shapes. In this case, we define the inputs as tensors with 3 elements of type float32. Doing this lets TensorFlow build a specific computation graph tailored to these inputs. Inspecting this concrete function reveals exactly how TensorFlow will execute the function for these particular input specifications. We print a summary of the inputs to the concrete function that was created by tracing. This concrete function is a specific version of the original traced function, with fixed input shapes and types. By examining these printed inputs, we can see the exact input specifications that the traced computation expects. This helps us understand how the function will work with data that has the same structure and characteristics. The code prints the output specification of the traced graph, which shows the shapes of the outputs that the traced function will produce. By looking at these shapes, you can see the structure of the data that comes out of the function. This helps you verify that the function is producing outputs in the form you expect. In other words, it is a quick way to confirm that the function's behavior matches your intended design. We use TensorFlow's function decorator to create a traced function that applies different behavior based on the input value. Inside this function, a TensorFlow conditional checks whether the input is greater than 0. If it is positive, the function returns the input squared, and if it is not, it returns the negative of the input. Using this conditional structure allows TensorFlow to trace the control flow and optimize the resulting execution graph. We define a TensorFlow constant with the value 2.0 and set its data type to float 32. This constant serves as a positive input for testing a function that uses control flow. Specifying the data type ensures the value works correctly with TensorFlow operations. It also helps maintain the desired level of numerical precision during calculations. We use a function called traced square if positive that takes a positive input tensor and applies TensorFlow control flow to decide how to transform it. The function checks whether the input is greater than 0. If it is, it returns the square of the input. If not, it returns the negative of the input. In this example, the input is positive, so the function produces its square, and that squared value is stored as the positive result. We define a TensorFlow constant with the value -2 and set its data type to 32-bit floating point. This constant serves as a test input for the control flow function. By using a negative value, we can observe how the function behaves and verify that it handles negative inputs correctly. When we call the function called traced square if positive with a negative input, TensorFlow uses a conditional operation to choose what to do. Because the input is negative, the function does not square it and instead returns its negation. This simple example shows how TensorFlow's control flow can make decisions based on input values. It also illustrates that this control flow can be traced once and then reused efficiently for different inputs. This example shows the output of a TensorFlow control flow function that either squares a positive number or takes the negative of a negative number. After computing the result, it uses a conversion method to turn the TensorFlow tensors into regular Python numbers so they can be printed. The key idea is that the traced function behaves consistently for different inputs while still allowing the results to be displayed in a familiar numeric format. At the end, the script prints a message confirming that the tracing demonstration finished successfully. This final message shows that the script ran to completion without runtime errors. It also provides a clear and simple indication that the execution process has reached its end. This script demonstrates how TensorFlow runs operations eagerly and how it traces them into reusable graphs. It first confirms TensorFlow and any available GPU, then creates two constant tensors and adds them with an eager function to show immediate execution. It then wraps the same addition in a TensorFlow function to trace the computation, calls it twice to illustrate graph reuse, and inspects the traced graph's inputs and outputs. Finally, it defines a TensorFlow control flow function that either squares a positive number or negates a non-positive one, and shows it behaves consistently for both kinds of input, ending with a successful run without errors. Core high-level APIs. Building models with Keras. In TensorFlow 2.20, Keras is the main high-level tool for working with neural networks, so you can build, train, and evaluate models without dealing with low-level tensor details. It lets you design models using intuitive ideas like layers and activation functions, much like sketching a model structure. You can begin with simple sequential models and later move to more complex architectures with multiple inputs and outputs, all within the same framework. This allows you to focus on how your model is structured and behaves, while TensorFlow handles the underlying computations and where they run. In TensorFlow 2.20, Keras provides a simple, unified way to compile, train, and evaluate machine learning models. You set the optimizer, loss, and metrics in one step, then run training with options like validation splits and early stopping. This makes it efficient to compare model architectures, handle issues such as class imbalance, and monitor validation accuracy. The same workflow applies across domains, including medical imaging, time series forecasting, sentiment analysis, and recommendation systems, making Keras a flexible tool for many types of projects. Keras in TensorFlow 2.20 combines ease of use with powerful customization, so you can add your own layers, loss functions, and training loops, while still using high-level tools like model saving and TensorBoard visualization. This flexibility lets different teams, from research groups to startups and data science teams, adapt Keras to their specific machine learning tasks. Keras serves as a central hub for model development, connecting smoothly to data pipelines, distributed training strategies, and deployment targets. As a result, it provides a consistent way to build, train, and manage the full lifecycle of your machine learning models. Python code, building models with Keras. This material introduces the basics of building models with Keras using TensorFlow for simple classification tasks. It explains how to define a model, set up its structure, and choose appropriate settings. It then covers how to compile the model so it is ready to learn from data. Finally, it shows how to train the model to perform classification using these core steps. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. It makes sure that this exact version of TensorFlow is available in the environment. This helps manage dependencies and keeps the code compatible with the library. It is especially important when the script relies on features or behaviors that exist only in that specific version. We start by importing 3 modules that support key tasks in our script. The operating system module lets us interact with the system, for example, to manage environment settings. The random module allows us to generate random numbers, which is important when we want reproducible behavior by setting seeds. The math module provides useful mathematical functions and constants that we can use for calculations throughout the program. We set a fixed seed for the random number generator so that any random operations in our code produce the same results every time we run it. In this case, using a seed value of 7 makes the sequence of random numbers repeat consistently. This consistency is important because it allows us to reproduce experimental results and makes debugging easier since the behavior of the code does not change from one run to the next. This script first tries to import TensorFlow, which it needs in order to run. If TensorFlow is not installed or cannot be imported, the program immediately stops and shows a message explaining that TensorFlow is required for the demonstration. By exiting early, it prevents the script from continuing without this essential library and avoids runtime errors later on. To avoid CUDA errors on systems without a proper GPU setup, the code disables GPU usage by setting a specific environment variable. This tells TensorFlow to ignore any available graphics cards and rely only on the CPU. As a result, the program can run reliably even in environments that do not have a correctly configured GPU. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that the intended version of the library is installed and accessible in your script. Confirming the version is important because different TensorFlow releases can change features or behavior. Ensuring the correct version helps maintain compatibility with your code. The code first checks whether any GPUs are available using TensorFlow's configuration tools. If it finds at least one GPU, it sets the model to run on the GPU, so computations use that hardware. If no GPU is detected, it automatically falls back to running on the CPU instead. This simple decision process helps the model use the best available hardware for performance. The code reports whether the model will run on a GPU or a CPU. Earlier in the script, it checks if any physical GPUs are available. If at least one GPU is found, it selects the GPU as the device. Otherwise, it falls back to the CPU. This message is then printed so the user knows what kind of hardware is being used for computation. We begin by loading the MNIST dataset using Keras tools. MNIST is a standard benchmark for image classification that contains images of handwritten digits. The data is divided into a training set, which is used to teach the model, and a testing set, which is used to measure how well the model performs. Each part includes images stored as arrays of pixel values, along with their correct digit labels. The code first prints the shapes of the training and test datasets before any pre-processing. This quick check confirms that the data has been loaded correctly and that its dimensions match what you expect. By verifying the shapes early, you ensure that later steps, such as reshaping or normalization, are applied to the correct data structure. This helps prevent errors and confusion in the rest of the workflow. For this quick demonstration, the code uses only a small subset of the training data instead of the full dataset. It limits the training set to the first 2,000 samples to make the process faster and easier to manage. The training images and their labels are sliced to create smaller datasets, which are then used for the example instead of the complete training data. The code first converts the training images to floating point numbers so they can be used in mathematical operations, then normalizes their pixel values to a range from 0 to 1 by dividing by 255. This normalization helps the model train more effectively and remain stable. The same conversion and scaling are applied to the test images so they are prepared in a consistent way for evaluation. To prepare images for a dense neural network, we first set the input size to 28 by 28, matching the total number of pixels in each image. We then reshape the images from their original two-dimensional grid into one-dimensional vectors using this input size. This reshaping is applied to both the training and test sets so that every image is represented as a single sequence of pixel values. In this form, the data is ready to be fed into the dense layers of the model. After reshaping the training and test datasets, we must confirm that their new dimensions match the model's expected input shape. The first check verifies that the training data has the correct shape, and the second does the same for the test data. These validation steps help detect any mistakes made during reshaping so we can be sure the data is properly formatted before it is passed into the model. We are building a simple neural network model using the sequential approach in Keras, which stacks layers in order. The model begins with an input layer that takes in our flattened image data. We then add a dense layer with 64 neurons and a ReLU activation function to learn patterns from the inputs. Finally, we include a dense output layer with 10 neurons, one for each class, using a softmax activation to produce class probabilities. Together, these layers form the basic structure of our classification model. This code calls the model summary function in Keras to display a compact overview of the model's architecture. It shows each layer, the shape of its outputs, and the number of parameters. The summary is printed line by line to the console using the standard print function. This makes it easy to quickly check how the model is structured and how complex it is. This step compiles the Keras model so it is ready for training. It uses the Atom optimizer, which is well suited for efficient learning. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the labels are integers. Accuracy is included as a metric to track how well the model performs during training and validation. We train the model using the Keras fit method with our prepared training data and labels. The model runs for 3 epochs, meaning it passes through the entire dataset 3 times. It uses a batch size of 64, so the weights are updated after every group of 64 samples. Training is run in silent mode with no progress messages, and 20% of the training data is held out as validation to monitor performance during training. This code checks how well the model performs on a small part of the test data. It uses the TensorFlow Keras evaluation function to compute the model's loss and accuracy. Only the first 1,000 test samples are used, so the evaluation runs quickly. The process is run silently without showing progress, and the resulting loss and accuracy values are saved as the model's performance metrics on this test subset. We first report the final training accuracy, taken from the last recorded value during training, to see how well the model fit the training data. We then report the final validation accuracy, which shows how well the model generalized to data it did not see during training. Finally, we measure accuracy on a small subset of the test data to get an external check of performance on new data. All accuracy values are rounded to 4 decimal places for clear comparison. This script shows how to build a simple neural network with TensorFlow's Keras tools to classify handwritten digits from the MNIST dataset. It sets a fixed random seed for reproducibility, disables GPU use for compatibility, and loads a small subset of the data, normalizing the image pixels and flattening them into vectors. The model is a basic sequential network, with one hidden layer using a rectified linear activation and an output layer using softmax for multi-class classification. It is compiled with the Atom Optimizer, trained briefly for 3 epochs, and then evaluated on a small test set. Finally, the script reports training, validation, and test accuracy to summarize how well the model performs on this digit classification task. Efficient data pipelines. In TensorFlow 2.20, the Data API is a key tool for building efficient input pipelines by creating dataset objects that manage sequences such as images or text. Instead of loading data manually, you define a pipeline that reads, transforms, batches, and prefetches data, and TensorFlow runs these steps efficiently in parallel. This approach is especially useful in tasks like medical imaging, where large image files can be continuously processed and augmented. As a result, batches are prepared in advance, so GPUs or TPUs stay busy and are not left waiting for data. TensorFlow's high-level data APIs make it easy to work with many kinds of data sources and pre-processing steps while staying well integrated with the rest of the framework. They treat data from local files, cloud storage, or streaming inputs in a unified way as dataset objects. You can chain together transformations that run efficiently as a computation graph, even when your model uses eager execution, so the code remains intuitive while the pipeline is optimized. In tasks like natural language processing, this allows you to move smoothly from raw text through tokenization, filtering, batching, padding, and prefetching to produce model-ready tensors with minimal overhead. In TensorFlow 2.20, efficient data pipelines are essential for scaling training across multiple devices or machines, and for working smoothly with advanced training and distribution strategies. These strategies automatically split the input data, so each GPU or worker processes its own portion without overlap, which is especially important for large-scale tasks like recommendation systems with massive datasets. By using features such as caching and prefetching, you keep frequently used data close to the computation and reduce delays, so each worker can handle its data slice efficiently. This design helps maintain high performance and consistent behavior, whether you are training on a single laptop or a large distributed cluster, and it simplifies complex data workflows throughout a project's lifecycle. Python code. Efficient data pipelines. This script introduces how to build efficient data pipelines in TensorFlow by first simulating the core ideas with simple Python lists. It focuses on the main operations used in data input pipelines, including batching data into groups, shuffling to randomize the order, applying mapping functions to transform elements, and prefetching to prepare data ahead of time. The goal is to show how these concepts work in a clear and accessible way before using the full TensorFlow data tools. In this part of the script, we would normally install any needed external libraries such as TensorFlow using a command run in a terminal. Installing TensorFlow makes all of its components available, so we can use it to build efficient data pipelines. However, in this script, the installation command is commented out, so it serves only as a placeholder or reminder and is not actually executed. We begin by importing the random module to add randomness to our program, which is useful for tasks such as shuffling data. We also import the itertools module, which provides tools for creating efficient iterators when looping over data. Together, these imports prepare us to build a data pipeline that can perform operations like shuffling and batching in an efficient way. We start by setting a fixed random seed using the random module so that any random operations in our script always produce the same results. This makes the behavior of the code predictable each time it runs. Such reproducibility is especially important when building and testing data pipelines because it allows us to reliably check and compare how the code performs over time. We create a simple synthetic dataset by first generating numbers from 0 to 19 to act as our features. For each of these numbers, we then compute the remainder when dividing by 2 to produce the labels. This gives each feature a label of either 0 or 1. The result is a basic binary classification dataset that is useful for demonstrating how data pipelines work. Before building the data pipeline, we first check that the number of features matches the number of labels. This is essential because each feature must have a corresponding label for the dataset to be valid. By enforcing that their lengths are equal, we avoid mismatched data that could cause errors or incorrect results later in the pipeline. The normalize feature function transforms an input feature value by subtracting 10 from it and then dividing the result by 10. This simple normalization shifts the data so that values are centered around 0 and scaled down. Such normalized features can help some machine learning algorithms work more effectively by providing data in a more consistent range. The normalize feature function takes a single feature value and applies a simple normalization step. It subtracts 10 from the input and then divides the result by 10. This shifts the data so it is centered around 0 and typically falls between -1 and 1. Such normalization is useful in machine learning because it gives input features a consistent scale, which helps make the learning process more stable. This function creates a randomized order of item positions by first building a list of indices from 0 up to 1 less than the number of items. It then uses the random module to shuffle these indices directly in the list. A fixed random seed is set so that the shuffling is repeatable and consistent each time it is run. Finally, the function returns the shuffled list of indices, which can be used to rearrange data in a random order. This generator function prepares data by taking in features and labels, then outputting them one pair at a time in a shuffled and normalized form. It first figures out how many feature items there are, then uses a fixed random seed to shuffle their indices for consistent randomness. For each shuffled index, it retrieves the matching feature, normalizes its scale, and pairs it with the corresponding label. These processed pairs are then yielded one by one, enabling efficient, streaming-style data processing. We define a function that groups a stream of samples into batches. It keeps two lists, one for features and one for labels, and adds each incoming sample to the appropriate list. When the number of collected samples reaches the desired batch size, the function outputs that pair of lists as a complete batch and then clears them to start a new one. After processing all samples, if any remain that do not fill a full batch, it outputs them as a final, smaller batch. This function is a prefetch generator that uses an internal buffer to handle batches of data more efficiently. It builds up a small list of upcoming batches, and whenever the buffer grows beyond a set size, it outputs the oldest batch and removes it from the buffer. After all input batches have been processed, it then yields any remaining batches still stored in the buffer. By keeping some batches prepared in advance, it helps simulate overlapping work and can improve overall processing efficiency. We start the data pipeline by running a sample generator on the raw features and labels for a small epoch, using a fixed random seed of 123. This generator shuffles and normalizes the data, and the fixed seed makes the shuffling reproducible for debugging and consistent results. The output of this generator becomes the base iterator for the rest of the pipeline, providing the foundation for later steps such as batching and prefetching. We use a batch generator function to group our data samples into small batches for processing. It takes an incoming stream of samples, in this case from the base iterator, and combines them into batches of 4. Batching is important because it lets us process several samples at once instead of handling each one separately, which is more efficient for large datasets. By batching the shuffled and normalized samples, we prepare the data for later stages in the pipeline, such as prefetching, which can further improve overall performance. We use prefetching in the data pipeline to overlap data loading with processing. A prefetch generator takes the batch data iterator and keeps a small buffer of up to 2 batches in memory. While the current batch is being processed, the next batch is prepared in advance. This reduces idle time between operations and makes the pipeline more efficient. We start by taking a few batches from the prefetch data iterator so we can inspect what the pipeline is producing. Using a tool to slice out the first 3 batches, we capture a small sample of the data. This lets us check that each processing step, including shuffling, mapping, batching, and prefetching, is working as intended. By examining these batches, we can confirm that the data is being processed and delivered correctly through the entire pipeline. We begin by printing the total number of raw samples, which is simply the length of the raw features list and gives an initial sense of dataset size. Then we print how many batches were collected, showing how many groups of data the pipeline produced. Finally, we preview the shape of each batch by going through them one by one and reporting the batch index along with the sizes of the features and labels. This quick inspection confirms that batching worked correctly and that features and labels are properly aligned. We begin by taking the first batch of data from our prefetched iterator, which includes both features and labels that have already passed through the processing pipeline. We then display the normalized feature values in this batch to see how the data looks after normalization. Next, we print the corresponding labels to confirm they match the correct features. This verification step is important to ensure that the pipeline has preserved the correct pairing between features and labels throughout processing. We rebuild the dataset by first creating an empty list that will hold pairs of features and labels. Then we loop through each collected batch, pair each feature with its corresponding label, and add these pairs to the list. This process keeps the features and labels correctly aligned, just as they were in the original data. At the end, we check how many pairs we have reconstructed to confirm that the total matches the original number of samples, which verifies that the pipeline has preserved the data correctly. This script shows how to build an efficient data pipeline in Python, similar to TensorFlow's data handling. It creates a synthetic dataset of features and labels, normalizes the features by shifting and scaling them, and shuffles the data with a fixed seed so results are reproducible. The pipeline then groups the data into batches of 4 and uses prefetching so data preparation can overlap with data consumption, improving efficiency. When run, it produces 3 batches of normalized features with their labels, demonstrating that the labels stay correctly aligned with their features throughout the process. This illustrates how to manage and prepare data efficiently for machine learning tasks while preserving order and alignment. Distributed training strategies. TensorFlow's high-level distribution APIs let you scale a model from one machine to many without rewriting your core code. Using the distribution strategy framework, you can start training on a local CPU or GPU, then move to a multi-GPU server or cloud cluster with only small changes. These strategies automatically handle device placement and synchronization, so you can focus on model design instead of parallel computation. This makes it practical to prototype a model on a single machine and later train it on multiple GPUs or TPUs for large-scale workloads. TensorFlow's distribution framework offers different strategies for various hardware setups while keeping a common interface that fits smoothly into model building workflows. On a single machine with multiple GPUs, the mirrored strategy copies the model to each GPU, splits each data batch, and then combines gradients so training behaves like using a larger batch on one device. For specialized accelerators such as TPUs, the TPU strategy coordinates training across TPU cores and is well suited to large models, including those in computer vision. In multi-machine environments, the multi-worker strategy spreads training across several servers, each possibly with multiple GPUs, to significantly speed up work on large datasets. TensorFlow distribution strategies let you scale deep learning models without changing your overall workflow. You place your model logic inside a chosen strategy and keep using the same training loops and metrics, while the strategy automatically spreads data and computation across devices or machines. This is especially valuable for teams that need to update models frequently, such as in healthcare analytics or recommendation systems. By using these APIs, teams can move smoothly from local experiments to large-scale training on clusters or cloud platforms, all while keeping a consistent codebase and achieving the performance needed for demanding tasks. Python code, distributed training strategies. This script gives a simple introduction to TensorFlow distribution strategies. It demonstrates the ideas using a very small model and synthetic data, so you can focus on how distribution works rather than on complex details. The examples are designed to keep the output short, clear, and friendly for beginners who are just starting to learn about distributed training in TensorFlow. The line beginning with an exclamation mark is a shell command meant to be run in a Jupyter notebook or similar environment. It uses the pip package manager to install TensorFlow version 2.20. Doing this makes sure the code runs with the exact TensorFlow version it was designed for. This helps prevent compatibility problems that might occur with different versions. We begin by importing a few standard Python libraries that support our program. The operating system library lets us work with environment variables and other system features. The random library is used to generate random numbers and can help make results reproducible by setting a seed. The math library provides mathematical functions even though it is not directly used in this example. Finally, the system library gives access to system-specific settings and tools, such as handling exceptions or exiting the program when needed. To make our results reproducible, we fix the sources of randomness in our program. We set the random seed in Python's random library to a specific value, and we also set the Python hash seed environment variable to the same value. Together, these steps ensure that operations affected by randomness or hashing behave the same way every time the code runs. This consistency is especially important in machine learning experiments, where uncontrolled randomness can lead to different outcomes and make debugging or verification difficult. We place the TensorFlow import inside a try-except block so that if the import fails, for example because TensorFlow is not installed, we can handle it cleanly. When an exception occurs, the program prints a message explaining that the import failed. It then exits safely using the system exit function instead of crashing. This approach provides a controlled and predictable shutdown when TensorFlow is unavailable. To avoid problems with CUDA when GPU resources are limited, the code sets an environment variable that turns off GPU usage. This forces TensorFlow to run only on the CPU. Doing so helps prevent errors related to GPU handles that can occur in restricted or constrained environments. This line displays the version of TensorFlow that is currently in use. It provides a quick check that the intended version of the library is installed and accessible in your script. Confirming the version is important because different versions may support different features or functions. This helps ensure your code is compatible with the TensorFlow environment you are running. The code uses a TensorFlow configuration method to check whether any GPU devices are available. This step identifies if the system can use GPU hardware. Knowing this is important because GPU support allows distributed training strategies to run much faster and more efficiently than on a CPU alone. The code first checks how many physical GPUs are available on the system. If more than one GPU is found, it uses TensorFlow's mirrored strategy to distribute training by mirroring the model across all GPUs. If there is only one GPU or none, it falls back to the standard non-distributed strategy. This automatic choice helps the training process make efficient use of whatever hardware is available. The code prints the name of the distribution strategy class being used, which tells you how the model is being distributed across available resources. By checking this name, you can confirm whether a specific strategy, such as mirrored strategy, is active, or if the default strategy is in use. This quick check helps you understand and verify the environment in which your model is running. We begin by setting up a simple synthetic dataset with 256 samples and 8 features per sample. This creates a small, manageable dataset that is suitable for demonstration. It still resembles a real-world scenario because each sample has multiple features. This setup lets us explore methods and concepts without the complexity of a very large dataset. This code uses TensorFlow to generate synthetic feature data by drawing random values from a uniform distribution. It creates a tensor whose size is determined by the chosen number of samples and features. A fixed seed value of 7 is used so that the same random values are produced each time the code runs, ensuring the results are reproducible. The code generates synthetic labels by summing each sample's features along the second axis, producing a single value per sample. This reduces the data to one dimension while still keeping it in a two-dimensional array format. The option to keep the original dimensions ensures the output shape remains compatible with later steps in the model training process. Before building the dataset, the code verifies that the number of feature samples matches the number of labels. This check ensures that every input has a corresponding output, which is essential for correct model training. By validating this alignment in advance, it helps avoid mismatches that could cause errors during the training process. We use TensorFlow's data tools to build a training dataset from our synthetic features and labels. The tensors are sliced into individual samples, where each sample contains one feature and its corresponding label. Organizing the data this way lets TensorFlow efficiently manage and process large data sets. This streamlined input pipeline supports faster and more reliable model training. The dataset is shuffled using a buffer of 256 samples to randomize their order, with a fixed seed of 7, so results are reproducible across runs. The shuffle order is not changed between epochs, which helps keep training behavior consistent and can simplify debugging. After shuffling, the data is grouped into batches of 32 samples, a common choice that improves training efficiency and manages memory use during model training. Within the strategy scope, we build a simple sequential model using Keras. It begins with an input layer that matches the number of features in our data. Pause. Then we add a dense layer with 16 units and a ReLU activation to introduce nonlinearity. Pause. Finally, we include a dense output layer with a single unit, which is suitable for regression tasks where the goal is to predict a continuous value. Within the strategy scope, the model is compiled to define how it will learn. It uses the Atom optimizer with a learning rate of 0.01 to update its weights efficiently. The loss function is mean squared error, which measures how close the predictions are to the actual values. During training, mean absolute error is also tracked as a performance metric. With this configuration, the model is prepared for training. The model is trained on the dataset for several complete passes called epochs. In this case, the training is run for 3 full epochs over the data. The verbose setting is turned off, so the training proceeds without printing detailed logs or progress messages. This keeps the console output minimal and focused only on the final or most important results. The code evaluates the model using a small batch from the dataset. It does this by calling the dataset iterator to get the next batch of data. This batch serves as a quick test set to check how well the model is performing. By using only a subset of the data, we can rapidly assess the model's current accuracy or behavior without running a full evaluation. In this step, we split each data batch into 2 parts. One holds the input features, and the other holds the matching target labels. This separation is essential because the model needs to clearly distinguish what it should use as input from what it is trying to predict. By organizing the data this way, we properly prepare it for evaluation or making predictions and ensure the model processes it correctly. Before evaluating the model, the code prints the shapes of the input and target batches to confirm that the data is structured correctly. This check makes sure that the inputs and outputs line up as expected for evaluation. By verifying these batch shapes in advance, you can catch mismatches or data preparation errors early and help ensure that the model evaluation runs smoothly. The model is evaluated on a batch of data to measure how well it performs. During this evaluation, 2 metrics are calculated, the loss and the mean absolute error. The loss is based on mean squared error, which reflects how closely the predictions match the true values. The mean absolute error reports the average size of the differences between predicted and actual values, giving a clear sense of prediction accuracy. The evaluation runs without extra logging, so the output stays simple and focused on these results. The code prints a brief summary of how well the model is training by showing the loss value for a small batch of data. It converts this loss to a clear floating point number before displaying it. This loss value indicates how well the model is performing on that specific batch and helps assess its training quality. This code prints the mean absolute error from the model's evaluation on a small batch of data. Mean absolute error, or MAE, is the average absolute difference between the model's predictions and the true values, so it gives an easy-to-understand measure of prediction accuracy. Converting the MAE to a regular floating point number makes the result clean and readable. and this value is then shown to the user for a quick check of how well the model is performing. To run a single prediction with the model, we start by taking one sample from the input batch. We then use a function in TensorFlow that adds an extra dimension to this sample, so it is treated as a batch of size 1. This step is required because the model is designed to receive inputs in batch format even when we only want to predict for a single example. To make a prediction on a single example, we pass that sample input through the trained model to produce an output. We call the model's prediction function with this one input and set the verbosity level to 0 so it does not print extra details. This turns off detailed logging and keeps the focus on the predicted result. In this way, we can clearly see how the model behaves on a specific case without any distracting additional output. This code prints the true label and the model's predicted value for a single data point. It takes the first label from the batch, converts it to a numeric value for readability, and does the same for the model's prediction. By comparing these two values, you can quickly see how closely the model's prediction matches the actual label and get a sense of its performance on that example. This script shows how to run distributed training in TensorFlow by first setting a deterministic environment and checking how many GPUs are available. Based on the GPU count, it chooses either a mirrored strategy for multiple GPUs or a default strategy for a single or no GPU. It then creates a simple synthetic regression task, builds a small sequential model with one hidden layer, compiles it with mean squared error loss, and trains it for a few epochs. After training, the script evaluates the model on a small batch to report loss and mean absolute error, and finally makes a prediction on one sample to compare the predicted value with the true label. The printed output summarizes the TensorFlow version, the chosen strategy, data shapes, evaluation metrics, and prediction results to give a compact view of how the model performs during training and inference. TensorFlow API landscape: stable and deprecated APIs. In TensorFlow, stable and deprecated interfaces reflect a balance between long-term support and planned retirement of features. Stable interfaces are those that TensorFlow team commits to maintaining with backward compatibility and consistent behavior across updates. This means that if you build systems using core components such as layers and optimizers, you can rely on them to keep working in future versions. Such stability is especially important for long-lived, high-stakes applications, and it forms the foundation for machine learning systems that must be maintained and scaled over time. In TensorFlow, deprecated APIs are older functions, classes, or modules that still work for now, but are planned for removal or replacement in future major versions. They are kept mainly for backward compatibility and are not recommended for new projects. These often include legacy training loops and layers that no longer match current best practices. When you see a deprecation notice, treat it as a signal to start moving your code to the newer, stable interfaces, so it will continue to work as TensorFlow evolves. Understanding the difference between stable and deprecated APIs is important for managing machine learning projects. Stable APIs are the right choice for long-term work because they are designed to keep functioning reliably in the future. Deprecated APIs may still be used in the short term, such as when replicating older academic studies or maintaining legacy industry models, but they should be treated as temporary. As newer models and tools prove more effective, deprecated code can be gradually removed, allowing stable APIs to support ongoing growth while easing the transition to modern practices. Model export and serving. In the TensorFlow ecosystem, the saved model format is the standard way to move models from research into production, and it is expected to remain stable and recommended in 2026. It works with TensorFlow Serving and TensorFlow Lite, so the same model can be deployed on servers, mobile devices, and edge hardware. Saved model stores the trained weights, the computation graph, and important metadata, which supports reliable use in regulated areas such as healthcare. For example, hospitals can deploy diagnostic models with confidence because this format is mature, well-documented, backward-compatible, and manageable for operations teams in production. In the TensorFlow ecosystem, older tools such as manually exporting frozen graphs and using session-based interfaces from version 1 are now considered outdated for new projects. These legacy methods may still run in existing systems, like a recommendation engine built around a frozen graph and custom C++ service, but they are no longer evolving. Engineers must decide whether to keep maintaining these setups or move to the modern, saved model workflow. Knowing that legacy approaches may lose support in future releases helps justify migrating to the stable, prioritized APIs in TensorFlow version 2.20 and beyond. TensorFlow is introducing experimental features for exporting and serving models, targeting new deployment scenarios such as advanced quantization, integration with new hardware, and on-device federated inference. These features can improve performance, for example on mobile GPUs, but their APIs may change over time. Because of this instability, they must be used with careful testing and strict version control. In practice, many organizations rely on stable APIs for critical workloads and explore experimental features only in controlled test environments. Python code, model export, and serving. This script introduces the basics of exporting TensorFlow models and how they are served in practice. It uses a simple setup that does not rely on external libraries, so the focus stays on the core export and serving ideas. The material highlights both the stable legacy export interfaces and the newer experimental style APIs, helping you understand how each approach works and how they relate to real deployment scenarios. We begin by importing 3 key libraries. The operating system library lets us interact with the system, especially for working with file paths and directories. The JSON library allows us to read and write data in the common JSON format. The random library provides tools for generating random numbers, which can also be made reproducible by setting a fixed seed. Together, these imports prepare our program to manage files, handle structured data, and use randomness in a controlled way. The code sets a fixed random seed using the random library so that any later random operations always produce the same results each time the script runs. This makes the behavior of the program predictable and repeatable. As a result, others can run the same script and reliably reproduce the exact outcomes. This reproducibility is essential when testing, debugging, or sharing experiments. Tiny linear model is a simple class that represents a basic linear model using a weight and a bias. When the class is created, these 2 parameters are converted to floating point numbers to keep numerical calculations consistent. With this setup, the model can make linear predictions by applying the weight and bias to input values. The predict method simulates how a model makes a prediction from a single floating point input. It does this by multiplying the input by the model's weight and then adding the model's bias. This calculation forms a simple linear transformation. Such a transformation is a basic operation in many machine learning models for generating predictions from input data. We create an instance of a simple tiny linear model to represent a trained model, giving it a weight of 2.0 and a bias of 0.5. These values define the linear relationship the model uses to make predictions. By setting these parameters, we simulate a model that is already trained and ready to be exported and used in serving demonstrations. We create a dictionary to represent a stable export of our model in a format similar to TensorFlow's saved model. This dictionary records the export format type, marked as saved model-like, and sets a version number that can help with compatibility or version control. It also defines a default serving signature that describes how the model maps its input to its output. Finally, it stores the model's learned parameters, specifically the weight and bias of our small linear model, so we can simulate exporting a trained model in a clear, structured way. We define a dictionary to represent a legacy export format that imitates the older TensorFlow 1.20 style. This format is described as frozen graph-like, meaning it resembles the frozen graph approach used in earlier TensorFlow versions. It specifies a simple computational graph with nodes named x, mul, add, and y. A note explains that this setup is meant to reflect the older graph style and is intended for use in legacy systems. We define an experimental export configuration as a dictionary that adds extra quantization metadata to a saved model-like format. This format is labeled as an experimental saved model style export and is currently at version 1, indicating an initial release. Within it, we specify a quantization section that uses an int8 per channel scheme, meaning the model's weights are stored as 8-bit integers separately for each channel. The overall status is marked as experimental, signaling that this export format and its quantization features are still in testing or development. This code creates a folder path where exported model files will be saved. It combines the current working directory with a specific folder name to define a consistent location for these exports. By doing this, it keeps all model outputs organized in one place relative to where the script is run. This code makes sure a target folder exists by asking the operating system to create it if needed. It specifies the base folder location and allows the creation command to succeed even when the folder is already there. By enabling this behavior, the program avoids errors if you run it multiple times or if the folder was created earlier. This makes the script more robust and easier to reuse. The function starts by using a helper that saves a dictionary as a JSON file. But first, it checks whether the dictionary is empty. If the dictionary has no data, the function raises a value error instead of saving it. This validation step ensures that only meaningful, non-empty dictionaries are written to disk. As a result, it helps prevent invalid or incomplete data from being stored, which could otherwise cause errors or confusion later. The code opens a file for writing with UTF-8 encoding so it can safely store text data. It then saves the export dictionary into this file in JSON format. The JSON is written with indentation to keep it structured and easy for people to read. This makes the stored data organized, understandable, and convenient to access later. We first build the full save location by combining the base directory with a specific JSON file name for the stable export. Then we call a helper function that checks the export dictionary is not empty and writes it to this file in an indented JSON format for readability. This procedure stores the model parameters and metadata in a structured way so they can be reliably loaded and used in the future. We first build the full save path by combining the base directory with a file named legacy frozen graph-like. Then we call a helper function that checks the legacy export dictionary is not empty and writes it to this path as a formatted JSON file. This workflow mimics saving a model in a style similar to older TensorFlow frozen graphs, which helps illustrate how models were traditionally exported. The code first builds a path for saving the experimental export by combining the base directory with a specific JSON file name. It then calls a helper function to write the experimental export dictionary to this file. Before saving, the function checks that the dictionary is not empty and formats the data with indentation so the JSON is easy to read. This process stores the experimental model export in a structured format for later use or analysis. To load a saved model, we open the file at its known location in read mode using UTF-8 encoding, so characters are handled correctly. We then use a JSON library to parse the file contents into a Python dictionary. This dictionary holds the model's parameters and metadata in a structured form. Loading this information is a key step in preparing the model for inference or any further use. We begin by safely retrieving the weights dictionary from the loaded, stable model data, using a method that returns an empty dictionary if the weights entry is missing. Then, we create a new tiny linear model using the weight and bias values taken from this dictionary. When we access these values, we again use a safe retrieval method that falls back to a default weight of 1 and a default bias of 0 if they are not found. This process reconstructs the model with the same parameters as the original, so we can confirm that it behaves as expected. We test the reloaded model by giving it an input value of 3 and calling its prediction function. The model computes the output by multiplying this input by its stored weight and then adding its stored bias. The resulting value is saved as the prediction. If this prediction matches what we expect, it confirms that the model's parameters were correctly restored from the saved version. We build a short set of summary lines to describe different model exports and highlight their key differences. The summary records the path of each export type, then notes the format used by the stable, legacy, and experimental versions. It also lists the available signatures for the stable export, counts the graph nodes for the legacy export, and reports the quantization scheme for the experimental export. Finally, it includes the prediction produced by the reloaded model when given an input of 3, giving a concise overview of each export's main characteristics and behavior. The code goes through each line in a prepared summary and prints it to the console. These printed lines highlight the main differences between the available model export formats and their key characteristics. As a result, the output provides a clear, concise overview of how the model can be exported and what outcomes each export option produces. This script shows how to export and serve a simple linear model in Python. It creates a tiny model with a weight and bias, then saves it in 3 ways: a stable saved model style format, a legacy frozen graph style format, and an experimental format that includes quantization metadata. These formats are written as JSON files in a chosen directory. The script then reloads the stable export, rebuilds the model, and runs a prediction for an input of 3, producing a value of 6.5. Finally, it compares the export styles by printing their paths, format types, available signatures, graph size, and quantization scheme to illustrate how different model exports can be managed and contrasted. Experimental API namespaces. Experimental namespaces in TensorFlow contain cutting-edge features intended mainly for researchers and advanced users before they become standard. These experimental APIs, available in 2026, may offer new training methods or hardware support, but they are not yet stable. Their design and behavior can change significantly or even be removed based on feedback and performance. As a practitioner, you should explore them with interest, but use caution, especially for projects that require long-term reliability. Experimental namespaces in TensorFlow are like a testing ground for new features that are not yet fully supported. For example, a team might try an experimental distribution strategy to scale medical imaging models across multiple GPUs and then share their results with the TensorFlow community. If these features prove useful and reliable, they may become stable, fully supported APIs. If not, they can be revised or removed. This setup lets TensorFlow innovate quickly while giving you a relatively low-risk way to explore new tools, especially in research or internal projects. When working with experimental APIs, you should stay flexible because their behavior and location in a library can change a lot over time. Plan for frequent testing and updates, and avoid relying on these features for critical systems unless you have a clear migration strategy. It is safer to use them in non-production contexts, such as research branches, and clearly mark that they are not ready for live use. Still, watching these experimental areas can be valuable because they reveal likely future directions and help you prepare for upcoming tools. In this lecture, you learned to summarize the core architectural concepts behind TensorFlow 2.20 and eager execution. Identify the primary high-level APIs in TensorFlow 2.20 and their roles. And distinguish between stable, legacy, and experimental TensorFlow APIs relevant in 2026. In the next module, Module 2, we will go over tensor basics. Thank you for your attention. See you all in the next lecture.